What up, Chem 101ers? Don't think for a second that I forgot about you. We've got things going here. It's took a little bit of getting up going time. But anyway, we're gonna pick things up right where we left off from before, but I'm gonna back up to this slide because there is one thing that I really want to review with you guys, and it's this little graph right down here. And the reason why I want to look at this one is because this captures kind of the like the basic like physical property or the thing that's happening that causes the next thing that we're going to talk about. So I want you to see what happens with chlorine with a molar mass of 70 and compare that to helium with a molar mass of 4. So chlorine, Cl2, 20 diatoms, huge compared to helium. Helium is like wee. It's one of the smallest that we have. And at the same temperature, right? Like so right here, oh, dang it. Right here, same temperature at 300. If you'll notice, the chlorine is moving at about, I don't know, what is that, 250-ish, 250 meters per second, which is fast. But if you look at helium, on average, most of those molecules are moving 11 or 1200, so significantly faster, orders of magnitude faster, because the helium is so small. And that is really important to know for what's coming up next, which is this. Let me see if I can figure out how to work this whole controller. We've already done that. We did that together in class. I don't know if you're paying attention, but it's this. Actually, maybe that. Oh, it's backwards. Gas diffusion. Now, diffusion is for gas is when like it's all a gas particle and they're just sort of like mixing in together. You know what I'm saying? There's like this entropy increasing from like, the random linear motion of gases and chaos and statistical probability. And so most gases follow this kind of crazy path, right? And so we can watch this happen with this stuff, ammonia and hydrochloric acid. Now these are both gases that we can dissolve in water. But if we took in 2 empty bottles, you put them right next together, and then the ammonium and the hydrochloric acid are going to make ammonium chloride. And this will always happen more over here by the hydrogen chloride because look, it's got a mass of 36 grams per mole as compared to ammonium, which is only 17. So because it's smaller and it's at the same temperature, because see how it's like it's in the same room, right? So it's all the same temperature. The ammonia is actually moving significantly faster. Hey guys, come here. Wow, there's here. Now get out of here. So the ammonia goes really fast compared to the hydrochloric acid, and that's clutch. Like, the idea is clutch for this. So what this is telling us here, that's rate, right? So the rate is inversely proportional to the molar mass. It's like an inverse square, but who really cares? What's really important to know is that it's opposite. So this means that as this gets bigger, as the molar mass gets bigger, the rate is going to get smaller. Dig? Does that make sense? And this is just a ratio. It's all we can do really here is compare the rate of 2 different gases diffusing through air, kind of thing. You know what I'm saying? So this helps us like predict the molar mass of something that we don't know. You just compare to how fast it diffuses to a gas that you do know about. Oops. Hey. Like this. Watch, pay attention. There's some questions here. I really want you to like lock in your noodle for a little later. Let's look.
So the question asks, if you were to put some cotton wool soaked with concentrated hydrochloric acid and some cotton wool soaked with ammonia into a tube, firstly, what would you see? Question 2,
Good question.
Write an equation for the product that is formed.
You should know that from the previous slide.
How can you explain why the product is formed closer to one end than the other?
You should know this.
Do the experiment now.
Let's go do the experiment.
Record our observation and think about the questions.
I don't know why all the good videos are from England.
Into the right hand side of the tube.
Yeah, you can see the product forming like right here already.
Hydrochloric acid. And into the left hand side of the tube, we just put some cotton wool that's soaked with concentrated ammonium.
Yeah. You see it yet? I don't see any. Oh, time lapse. Thank you.
As you can see,
Totally see that.
we get a ring of white ammonium chloride formed.
If you notice, it's really far away from
The
the ammonia.
hydrochloric acid
Yep.
and the ammonia diffuse along the tube, and where they meet, we get the NH4Cl, the
Totally.
ammonium chloride.
Totally get that. You get that? I get
Because
that. That
ammonia
seems very clear.
is lighter than hydrogen chloride, the ammonia gas diffuses quicker and further along the tube, which is why the ring is further away from the end with the ammonia ring, it's closer to the end with the HCl on. Now we've done the practical.
Ha ha ha! But you better pay attention. It's going to be a good question for you to know. So the next thing we're going to talk about is effusion. Now, effusion is a little different than diffusion, because like I said before, diffusion is when gases are just sort of mixing together. Effusion, if you look at a pictogrammy here, shows you, it's basically when gas goes from a container full of gas to a container where there is no gas, so it's like going into a vacuum. So it doesn't need to work against any other gas particles. It just goes. Do you understand what I'm saying? However, the faster it effuses, if you can imagine this, as it goes from the container on the left to the container on the right, it sort of slows down until it reaches an equilibrium because of all the collisions and bouncing back and forth and things like that. And for that, we have this wonderful little equation. It's almost the same thing, but like opposite. So again, it's just a ratio between two different gases. And for this one, the rate is inversely proportional, like this time directly inversely proportional to the time that it takes. So that means that if the time is small, the rate will be big. If the rate is small, like that means that like the time is big. So small rate, like slow, like small as in like slow. I guess that's what I'm trying to say. If you have a slow rate, then you have like a big time. Does that make sense? I don't know if it makes sense, but there's the math. Math all looks really good. We use it for prediction. I think this is what we're going to be using mostly because that's what we're going to be measuring better, which is sort of like almost the exact same as everything else. All right, so this is example 5. I'm never going to get this right. That is example 517. I'm going to upload a separate video for that one, and then I want to look at this. So I've been saying that PV equals nRT for a while, and we've been saying, according to Avogadro, that like all gases are basically the same, and they are basically the same unless they're not. So basically, what this is telling us is that when you increase the pressure of these gases, like let's look at this one because this one's really freaky. Like ammonia. Ammonia is a very polar molecule. Does that make sense? So as you increase the pressure, basically what happens is the intermolecular forces of attraction begin to take over, and they sort of decrease the pressure and the volume. Right, the pressure volume thing sort of like gets smaller. Because as they're getting closer, they're kind of pulling on each other and whatnot. But if you look, once we really wickedly start increasing the pressure, I mean, that's a ridiculous amount of pressure down there, like 200 atmospheres. That's stupid. However, when that happens, you start seeing a bit of a repulsive force happen. Then there's like the whole electron cloud thing comes into play. But I mean, you and I are not gonna be living in this pressure zone. We are going to be existing right in a little teeny zone right there. Okay, so this is how real gases deviate from the ideal gas law. Even hydrogen starts to deviate. But if you notice with hydrogen gas, it is perfectly nonpolar, so it doesn't do any of that dipping down to have some kind of attractive force at all. It just shoots straight into repulsion because of electron clouds. And this is kind of what's going on. If you look at this little red particle and pretend like that's the particle that's going to be smacking against the container, causing pressure and expanding it to like make volume, right? Because I mean that's how a ample of gas has volume. It's because the particles are pressing on the sides that like push it open, like in a balloon. But if you can imagine, all those gases are like, as it's zinging towards the side of the container there, all these other gas particles that are inside there are pulling that gas particle towards itself. So the one that's about to hit the wall is sort of being pulled back. by all those others inside of it. You know what I mean? It's like kind of being pulled back. So when it slams into the side of the container, it's not hitting with all of its force because it's being pulled back by those intermolecular force of attraction from the other gas particles inside the gas sample. Does that make sense? Like that's kind of why things deviate when they have like polar structure and intermolecular forces of attraction. Those intermolecular forces of attraction just like mess with stuff. You get what I'm saying? Also, not for nothing, they're made out of electrons and protons, and so there's all kinds of weird repulsion things and attractive stuff that happens. But we do have a way to make up for this. And there it is, right? Shmeaw. This is an adjusted ideal gas law, and we call this the van der Waals equation. Van der Waals are we've called them dispersion forces in Regents class. It's basically attractive forces that hold nonpolar substances together. They're basically like really micro intermolecular forces of attraction, and we've just corrected for it. And if you look over here on table 5.4, which you don't have to memorize because it's right there in your text, I'll give it to you for the exam. Let's not, you know how this works. Don't freak out. We have, see how there's A, so for gas, this helium, like right here, if it was helium, the variable A, which goes right here, would be 0.034. And the variable B, which for helium appears to be 0.237 or something like that. 0.237 goes right meow, and that's how we can correct for the actual intermolecular forces of attraction that happen in all gases actually. When does this matter? I don't know. When it does, go talk to Damaris. He'll tell you when it really matters. Or if you ever go into surgery and they go like, put that mask over your face, and you're like, breathe deep and count backwards from 100, you might want to make sure that they've accounted for the van der Waals equations, because I think we talked about that. Could you imagine waking up because in the middle of surgery because somebody didn't like account for the van der Waals forces, the intermolecular forces of attraction for polar molecules and just non-polar molecules? No. So we make the corrections when necessary. Dig dug. All right. So here is another sample problem. It is sample 518. I'm not going to do this here because it's stupid, but I will upload a video doing that for you so we can go through it. And it's pretty simple. Your ideal gas equation is PV equals nRT, and for the van der Waals equation, sorry, don't look at that. The van der Waals equation is this thing right here. That's it. It's just like plug and chug. It's all there is to this. We're not like asking you to do all kinds of crazy derivations. Just plug and chug. That's it. I will upload something for that, but like you saw, sorry, not sorry. So here's what I want you guys to do for this for this homework. Here's how it's going to work. On Google Classroom, I'm going to upload an assignment, and it's going to be called homework 578 to 594. And what I want you guys all to do is to write this stuff out in hand, like your notebook, just like you did every other time. But I want you to take a picture of it and upload it to the homework assignment. Super easy. You can just like hand in homework assignment, attach photo, bing, bang, boom. Bing, bang, boom. You're done. Got it? That way I can look at it, I can grade it, I can make comments. It'll all be spectacular, and you're going to love it. All right, guys. I'll see you soon.